Well, good evening, everyone. This is the Michigan State University Science Festival statewide astronomy programming continuing, and we have a couple of more talks scheduled for later this evening. I am pleased to be joined by Jack Daleske of the Roger B Chaffee Planetarium located in Grand Rapids, Michigan, and I'm looking forward to his talk. If you have questions for Jack throughout the talk, you can put them in the Q&A of the Zoom webinar if you're listening on Zoom. And if you're listening on Facebook Live, you can enter your questions in the comments section, and we'll get to those as we go along. So welcome, Jack. I'm excited for your talk. What are we talking about tonight?
Thanks a bunch, Roxanne. So the title of our show is Earth's Place in Space. And so we're going to be talking a little bit about Earth's climate, and we're going to compare it to some of the other planets in our solar system. And just kind of a spoiler, we're going to find out how important the atmosphere is to our climate. And so, as Roxanne said, if you have any questions or something comes up, go ahead and type that into the question and answer section. And actually, I might ask some fun things along the way. So if I ask you something, feel free to just type in the chat, what you think the answer is, and I'll try to respond to you as I go. But we'll also have time at the end where we can have a little bit more of an open discussion and answer any questions people might have. And so what we've been working on, we've been working on it for quite some time, but this is going to be a new planetarium show that we will have for school groups starting next fall, called Exploring Atmospheres, and it'll accompany our Habitat Earth show. So we're going kind of into more of a planetary science that is, studying the Earth as a planet and how that can help us, how that's relevant to us human beings. So as we look around our dome right now, and what's also kind of cool is we set up a new way for us to kind of stream our planetarium to people, because we had to adapt to the past year just like everyone else. But as we look around our dome here, we might see different parts of day-to-day life. So we can see maybe some cool coos, some cows, and some of the city in the background. And as we see stuff, we're going to be talking a little bit about greenhouse gases. So if you see something that you think is a source of greenhouse gas emissions, why don't you go ahead and type that into the chat and maybe explain what the greenhouse gas is, or how, what the effect of it is. So we have some cows, we have the city, and we have some other things. If we look around, we can see some wind farms. Do those emit greenhouse gases? We can see power plants in cities, and if you look carefully, you might see some airplanes flying overhead as well. So this is what our Earth looks like from our point of view here on Earth, but we are going to explore Earth's climate, from a slightly different perspective. And we're going to explore our atmosphere from a different perspective. And so the atmosphere of our Earth is a layer of gases that surrounds a planet, and it's held in place by the planet's gravity. And greenhouse gases, there's a lot of different kinds of gases in that atmosphere, but greenhouse gases are certain gases that absorb heat and then re-emit that heat to make the Earth's surface hotter than it would be without that gas. And so the most important greenhouse gases that we're going to talk about today are carbon dioxide and methane. But before we talk about carbon dioxide and methane, we are going to blast off into outer space, and we are going to look at the Earth from another point of view. So hold on to your seats, because we're blasting off. And that's one of the things I really appreciate about the planetarium, is that we have a certain perspective walking around on the surface of the Earth, and it's kind of nice to fly out into space and to look at our world from a different point of view. And so when we look at our Earth from this point of view, one thing really stands out to me, and that's actually how small our atmosphere is. So when you look at the Earth is very, very large. It's about 7,900 miles in diameter, from end to end in diameter. But the atmosphere is not that big. It's a thin envelope sitting on top of the surface of that Earth. And 99% of all the air molecules and all the water molecules that are in our atmosphere are in the lowest 53 miles. So that's what most of our atmosphere is about 53 miles. And I'm actually gonna, let's highlight a section of our atmosphere and kind of get a closer look. This is a picture of the edge of the Earth from the International Space Station. So the International Space Station, 6 people are living in outer space right now in low Earth orbit. And the ISS is about 250 miles above the Earth's surface. And so this is what the atmosphere looks like to the ISS. And you can see, kind of the corner, you can see the solar panel, and you can actually see what are the northern lights. So the northern lights are kind of that upper atmosphere, that upper edge of the atmosphere. So that's our entire atmosphere, is that tiny little sliver that we just zoomed in on. And by the way, the ISS, it's 250 miles up. That's not very far away either. When I drive to visit my parents, I drive farther than 250 miles. So I like to say space is not that far away. It's just very hard to get to because you have to go straight up. And so the sun is the ultimate source of heat and energy for all life on Earth, but the atmosphere plays a really important role in how hot the Earth ends up being. And so we're going to fly away from the Earth now, and we're going to compare the Earth to some of the other planets in our solar system. And we're mostly going to focus on what we call the Earth-like planets. Those are the small rocky worlds that are near the sun. These are small rocky worlds. Some of them have atmospheres like the Earth. And we compare these Earth-like or terrestrial worlds compared to the gas giants, which are a very different kind of planet. So we're just going to be looking at these terrestrial, these Earth-like worlds. Right here, we have closest to the sun, we have Mercury, then we have Venus, then we have Earth and Mars. And so here we have another chance for people to show off their space knowledge. What is the hottest planet in our solar system? So go ahead and type that in if you think you know it. And if you think you know why, you can explain why too. And it's a bit of a trick question. And the correct answer, I'm going to delay for another second. The correct answer is actually Venus. Venus has an average temperature of about 420 degrees Celsius. I'm sorry, 460 degrees Celsius. And that's very, very hot. 100 degrees Celsius is boiling water. So this is about 4 times hotter than boiling water. Really, really hot. And it's about that temperature day and night with very little seasonal variation. And so a lot of people, they might say Mercury. And Mercury is a good guess. So Mercury is the closest planet to the sun. So it's getting the most heat and the most energy from the sun. But Mercury, we see a very big difference in the average temperature. So Mercury can be as cold as negative 170 degrees Celsius, colder than the coldest winters on Earth, or it could be about 420 degrees Celsius. So again, hotter than a pizza oven, very, very hot. And we'll kind of explore why that is. And really the short answer is Mercury doesn't have an atmosphere and not an atmosphere with greenhouse gases in it. Earth, for comparison, has a little bit of variation. So Earth will be about negative 25 degrees Celsius to about 45 degrees Celsius. So that's kind of our average temperature. And then if you can take a guess now, Mars is farther away from the sun, and it receives less heat and less light from the sun, and it has a much thinner atmosphere than the Earth. So if you had to guess, do you think that Mars is hotter or colder than the Earth? Oh, and thanks to everyone for who participated in that last one. And if you got Venus, then you were correct. So good job on that one. So Mars is actually on average colder than the Earth, because and that makes sense. If you guess that, it makes sense. It's negative 87 degrees Celsius to about negative 5 degrees Celsius. So on average, much colder than the Earth. But let's fly into these worlds and let's take a look at why that might be. So let's go to Mercury first. And so as I said, Mercury, it is the closest planet to the sun. Mercury is about 58 million kilometers from the sun. So the Earth is about 3 times farther away from the sun than Mercury. And Mercury is really, really hot during the daytime. It's about 427 degrees Celsius during the daytime. And again, that's hotter than a pizza oven, way hotter than boiling water. You'd fry in that temperature. But that's only during the daytime. That's only when you can see the sun shining down on you and you're getting that direct radiation from the sun shining on you. You're getting that direct heat, that direct light, and so on. But Mercury doesn't have an atmosphere, so it doesn't have a way to transfer that heat from one side of the planet to the other. So on the daytime side of Mercury, it'll be about 427 degrees Celsius. But on the nighttime side, as soon as the sun sets, as soon as the sun isn't shining directly on you, it'll drop to way colder than the coldest winters on Earth. And that's kind of a similar story to like the moon. And so people say, or if you're doing a spacewalk on the ISS, you have this, the astronauts are wearing this spacesuit because it can get really, really cold, but you come out from behind the Earth and you're in the sun's light, it gets really, really hot too. So, but then there's no way to transfer heat, so it gets complicated. But the important key here is the atmosphere. And we see the same thing on the moon because the moon doesn't really have an atmosphere. It can get boiling hot when you're in the sunshine and then freezing cold the second you're not getting that radiation. Venus, on the other hand, is about 460 degrees Celsius year-round, day and night, no seasonal variation. And this is because Venus has a really thick atmosphere of greenhouse gases. So we're going to fly into Venus now, and we're going to fly through this atmosphere. And this atmosphere is 97% carbon dioxide, which we know is a greenhouse gas. It's 97% carbon dioxide. So it's an atmosphere, but you wouldn't be able to breathe it. And the pressure from this atmosphere is actually much thicker than the Earth's atmosphere. So this atmospheric pressure is about 92 times greater than the pressure of the Earth's atmosphere. So I think of walking around on Venus would be like walking around at the bottom of the sea with all this weight pressing down on top of you. And that's kind of what it would be like to walk around on the surface of Venus. So it's really, really hot. You'd get crushed by the weight. It does rain on Venus, but it doesn't rain water. It rains sulfuric acid. So not a place I would like to go on vacation, to say the least. And so if we look around on the surface of Venus now, a lot of people do think that Venus may have looked like the Earth once. We see a lot of evidence that there was liquid water on Mars, on Venus in the distant past, billions and billions of years ago. Maybe 3 to 4 billion years ago. But there's no liquid water on Venus right now, and it's hard to imagine it was ever habitable, and it definitely doesn't seem habitable now, at least to any life that we know. And we believe that this is due to a runaway greenhouse effect, and it was a kind of runaway greenhouse effect that's far more severe than what would be possible on the Earth, just because Venus is closer to the sun, and it had all of this carbon dioxide, and we think also the water played a role when it was still present. And then now we will go to Mars, and as I pointed out, Mars is farther away from the sun than the Earth. It's got a thinner atmosphere, mostly carbon dioxide, but much thinner than the atmosphere, so it's a little bit more of a vacuum than the Earth. And it ranges from about negative 80 degrees Celsius to negative 5 degrees Celsius. So usually much, much colder than the Earth, but not always. And so my example there is during the 2019 polar vortex. So a few years ago, Michigan got as cold as negative 30 degrees Celsius. So that's colder than the Martian summer. So parts of Mars were warmer than parts of Michigan. So, it depends on the season. Mars has seasons just like the Earth does. And it doesn't have any liquid water anymore, but because it is colder, it does have frozen water, mostly on the North Pole and the South Pole on those ice caps. So when planetary scientists study other star systems, and we really only have one star system to compare these to. We compare it to our own. So when we look at other stars and planets that are orbiting other stars, we use a concept called the habitable zone. And so the habitable zone is the area around a star that's theoretically the right temperature for liquid water to exist on the planet's surface. And this is very theoretical. It's theoretical. It's defined by the temperature of the star. So hotter or colder stars would have bigger or smaller habitable zones. And if you look on our map right here of the habitable zone of our star, you see the Earth is right in that habitable zone. We see that Mars, by some definitions, is right on the outside edge of that habitable zone. And maybe by some definitions, Venus is kind of on the inside edge of that habitable zone. But by other definitions, it's a little bit smaller than that. But, I think of this as the Goldilocks zone is sometimes what we call it, because it's just like Goldilocks. It's not too hot, it's not too cold, it's just right. And the thing it's just right for is liquid water and all life as we know it. And so when we look at this, and Mars is technically in that habitable zone, Mars doesn't have liquid water, and neither does Venus. So it's important to realize that, while the temperature of the sun plays a role, by far the really important thing that we're talking about right now is the atmospheres. The atmosphere of a planet will push it to be more like Venus or more like Mars, depending on what gases we have in that atmosphere. And so let's bring it now back to greenhouse gases. So greenhouse gases, they absorb heat and then re-emit heat, and they make the planet hotter than it would be without it. So the way I think about Earth is that if we had no greenhouse gases, it would be about 0 degrees Celsius. So it would be freezing cold on Earth, and sometimes it'll be much colder than that, sometimes a little warmer. And then the average temperature right now is about 15 degrees Celsius. So in Fahrenheit, that's, I think, about 60 degrees Fahrenheit. So just the right temperature for us to enjoy on average. But that's not our problem right now. Our problem right now is that there's too much greenhouse gases being added to our atmosphere by human pollution. And the two most important examples of greenhouse gases that we're going to talk about right now are methane and carbon dioxide, which are both being released into the atmosphere at an increasing rate due to human pollution. And just to take carbon dioxide as an example, we believe, based on what we do, is we just had a exhibit actually called Under the Arctic at the museum. It was talking about the different kinds of science experiments that people are doing in glaciers and permafrost. So one of the things they do is they drill in and they get core samples from the ice, and so that we can learn about what the atmosphere was like hundreds and sometimes thousands and tens of thousands of years ago. It's really quite incredible. And so in the 1750s, so before human industrialization started, the amount of carbon dioxide in the atmosphere was about 280 parts per million. And it's about 415 as of 2019. So that's about a 45% increase very, very quickly, just because we humans are using carbon dioxide and fossil fuels. And as we just saw with Venus, carbon dioxide bottles in the sun's heat and holds onto it, and insulates it. And so that increases the temperature of a planet. And so what we're going to use right now is we're going to use a model of global warming and a global based on local temperature averages. So the baseline right here is actually the year 2000, which is kind of arbitrary, but that's what we use for our baseline. And so the tones that are a little bit more orange and red are going to be hotter than the local average in 2000, whereas the greens and blues will be colder than in 2000. So let's start off right at the beginning of industrialization, just about, the data goes back to about 1870, and let's see how the temperature of our planet has increased over the past 200 years or so. And this model is going to keep on going, and it's going to extrapolate based on what we have done in the past. And it's going to assume that we are just going to keep increasing the amount of CO2 we release into the atmosphere until the year 2100. And actually, just to pause right here at 2021, because last year and the year before that, we're breaking records for how hot each month was. So, when we talk about these really hot temperatures, we are talking about changes in extremes. So maybe in 22 or 2023, maybe it'll be a colder than average year. We understand that these are differences in extremes, but there's a really clear trend that kind of keeps on going past that. And so if we keep releasing carbon dioxide in the atmosphere, you can see it gets really hot really quick. And so we are already living through climate change, and so we have a really clear idea of what to expect. In Michigan, for example, we see more extreme weather changes due to climate change, increasingly frequent extreme floods, extreme heat waves, and all of that damages our farms, our lakes, our cities, and it causes millions of dollars in damage. Just with more extreme weather, we end up paying for it one way or the other. And over the next 20 years, we're expecting the number of days that are extremely hot, the number of days that are above 90 degrees Fahrenheit in Michigan will quadruple, and the number of warmer winters will turn our heavy snow into heavy rain. So we're in a pretty good spot. Other places closer to the equator are going to be much harder hit, and they will deal with even more extreme temperatures. And it's going to be a really negative impact for everyone all over the globe, but it doesn't have to be that way. And so let's see another scenario now. And this one, it shows a gradual reduction in CO2 emissions starting right now. So the idea is we're going to keep on releasing CO2 in the atmosphere, but we're going to slow down the rate at which we're doing it. So we're not going to increase the rate that we are going to release CO2. And so it's too late to stop climate change, but we can mitigate the worst effects. So let's just real quick see that. Oh, it went dark. So let's give it just a second to think. Let me pull that back up. There we go. So let's look at this other model, this more optimistic model, where we make positive changes to our society. And as we kind of look at this, let me focus it back on North America so we can see the difference. So we would have to make major positive changes to fight climate change. And so if we have some time right now, maybe you can type into the question and answer or into the Facebook chat. What do you think that you can do to reduce our greenhouse gas emissions? And what can we do individually? What can we do as a society? What do you think is important to you? And if there's any questions on the Facebook page, Roxanne, please feel free to share that with me. Personally, I think the most important thing to do is green energy, because that's our most important step to fighting climate change, but also protecting biodiversity in the Earth's forests and the oceans. And the forests especially, they really lock away that carbon because trees are made out of carbon. So if we have lots of forests, that's locking away that carbon so it isn't in our atmosphere. So that's right there, our greatest ally, I think, are protecting forests and protecting forests. But somebody said switching to solar power for our house. I really want to do that someday. That's my big goal personally. But until then, I try to bike to work every now and then. I work pretty close to my home, so biking to work is really easy for me. And somebody said electric cars or biofuel cars. That's another great example. And People will point out for electric cars, sometimes if the electrical grid isn't on green energy, maybe if you're burning coal or fossil fuels or something from the electrical grid, maybe that doesn't have an immediate help. But a lot of scientists feel very confident that by electrifying as much as possible that's using fossil fuels right now, that makes it easier to switch over to green energy at a society level. And it's funny, I drive through Illinois, like I said, to visit my parents, and just the number of windmills that I see that I just know weren't there 20 or 30 years ago. That, at least, that's one of the things that makes me very hopeful. I see the amount of windmills out there in the plains.
Jack, has there been any data coming in about, since we all, with the pandemic, I guess one of the silver linings to this dark cloud was people stayed home and didn't drive. Have they noticed any shifts in climate?
That's a great question, and unfortunately, I don't have any data, any real data to support that one way or the other. I'm inclined to believe it, and I heard lots of anecdotal stuff about animals just having a little bit of a better time of it because not as many people are commuting and so on. And so I certainly would believe it, and I certainly think that that's one potential option, is to not commute. If we can find a way to not spend hours in the car every day, that's a great way to make things better. So I feel like it has to have done something, but that's just my opinion. Yeah, thank you for the question.
And then we did have one more comment in the Q&A from M. He said the sky was cleaner for a while overseas and in Asia.
Yeah, that makes a lot of sense too, because when we talk about this kind of pollution, it's also can be very local. So right where you're emitting, where you have the buses and the cars and stuff like that, it's a lot there. So it's really cool. Well, thank you for contributing, and thank you for typing stuff into the question and answer, so I don't feel like I'm talking to myself. I hope people enjoyed it. So this was based on data from a few different places. Let me see if I can point our camera to our. I don't think you'll be able to see our data, but the data came from the National Oceanic and Atmospheric Administration. GFDLA is the name of the model, and so we had some fun. We were inspired by a system called Science on a Sphere that works with different museums, but they made a lot of their data freely available, and that kind of worked out well for the planetarium. And so we're kind of interested in doing more Earth science stuff like that. So if you have any feedback for us on this, I'd love to hear it, and hopefully we will do more stuff like this in the future.
And is the planetarium open now, or not quite yet?
Yes, thank you for asking. We're open right now. We're at a little bit less than 50% capacity. So we have social distancing set up, and we ask that everyone please wear their masks. But we got a lot of different shows going on right now, including Under Starlit Skies, which is always the show I recommend if people haven't been to the planetarium before, because that is that's kind of our star talk show with a live presenter, and it's very interactive, and you can learn the stars and constellations that you want to find in the night sky tonight. We also have on weekends One World, One Sky, which is our kids show with Big Bird and Elmo. And then we have Incoming, which is all about asteroids during the week. And then on weekends, we got the Queen Light Show. So I know people were asking about the light show and if we were going to be doing those again. So we brought that back for the weekend. Really excited to be back open.
Oh, I may have to come out to see the Queen Light Show.
It's fun.
And then M wants to know where the planetarium is located.
Oh, well, the planetarium is at the Grand Rapids Public Museum. So that's right in downtown. And let's see, I don't know if this will work, but. I don't think I can show it. I was going to try to fly into see Grand Rapids on the Earth, but I don't think I can do that right now. That's not going to work out. But yep, right downtown at the Grand Rapids Public Museum.
Awesome. And then Jeff wants to know, I keep mentioning Facebook live feed. If you go to the MSU Science Festival Facebook page and just click on the live video, you'll see it there. Or if you go to the MSU Science Festival website, which is sciencefestival.msu.edu, there is a Zoom link there for the next presentation, which I should know when that starts, but I have to check my cheat sheet here. That one starts at 7 o'clock. And then we have another one starting at 7:45. Awesome. Well, thank you, Jack. This has been really informative, and we all can do our part for climate change. This is the only world we have, so we want to keep it safe. We want to have air we can breathe and enjoy the countryside out there. Looks like, okay, Jeff found the live feed. Awesome. And then we just got a lot of thank yous, so we do appreciate it. And if you get a chance and are in Grand Rapids, check out the planetarium there. I know I plan on heading over to see Queen.
Awesome.
Awesome. Thanks a lot, Jack, for sharing.
Yeah. Thank you, Roxanne, and thanks, Jeff, and everyone for participating. Makes it more fun for us too. So hope you enjoy the rest of the Science Festival.
All right, everyone have a good night, and we'll see you on the next talk. Or we also have things going all throughout the month of April still. And tomorrow we have a big expo day with 50 talks lined up. So check us out. All right, everyone have a good night.